everyone. Welcome to this webinar. My name is Dr. Royce Liu, and I work at the Christchurch office of WSP in New Zealand as a bridge engineer. And today I'll be presenting some of my work that I've undertaken with some of my colleagues in the development of the Composite Timber Hybrid Bridge, a novel solution for a low carbon future. If you're interested in knowing what I look like, that's what I look like. My title's not quite right there, but yeah, don't worry about that. In terms of the agenda, I have 6 sections. We'll start off with the background of the presentation, the motivation for this work. Then I'll talk about the proposed composite hybrid system. Following on that, I'll talk about the Superstructure design study to compare its structural characteristics and material quantities against more typical solutions. Then I'll present the results of that study, and then do a short discussion on balancing design considerations in the context that we're trying to be more strong in our focus on sustainability. And then lastly, I'll present the conclusions. Okay, so as you all know, one of the major challenges in the transport sector or civil engineering in general currently is our carbon emissions. We use a lot of very carbon intensive materials as well as processes, and some of these materials need to be transported large distances as well, contributing about I think it was 15% to the global carbon emissions. Now, one way to get around this is to use lower carbon materials, and one of those materials is timber, which has made a bit of a comeback since its more primordial use for bridge construction. However, even though timber does have a lot of benefits with respect to it being lower carbon and sustainable, it has quite a few challenges in its implementation in bridge structures in particular. For fully timber bridges, I see 3 main challenges currently to its widespread implementation. One of those is guaranteeing 100-year durability. This is quite dependent on the treatment of the timber, design details, as well as the climates that the timber is in, and any external influences that could affect its integrity with time. Next is trying to minimize damage under extreme loading, such as flood debris. Timber is not as ductile as, say, steel, as well as in a fully timber bridge, providing a strong diaphragm to transfer lateral loads can be challenging in comparison to a concrete slab. And lastly is, I guess, very important for the usability of the bridge and for roads, adhesion of the timber with surfacing materials for resisting heavy traffic. We don't want to need to be closing the bridge every 20 years, every 5 years to resurface. especially if these bridges are widespread throughout a network, it can cause significant impacts. So some possible ways to get around those issues is to use partially timber bridges. So one of those is Timber Concrete Composite on the top picture. This was developed in the USA, and some bridges are over 80 years old. Because it has a timber deck that's composite with concrete beams, the surfacing adheres well with the deck because it's concrete, as well as the timber is sheltered by the concrete deck as well. However, the solution is limited to short spans due to the higher dead loads required to be carried by the timber beams. Another partially timber bridge solution is using steel girders with timber decking. This has been commonly used in New Zealand on low traffic routes in the past. It's confined to short spans as the deck is not composite with the beams typically. And it has issues with maintenance and poor adhesion with the surfacing. As I said previously, surfacing doesn't adhere very well to timber. So the question is, how can timber be used to reduce the embodied carbon of new bridges while satisfying current design requirements and constraints to reduce barriers to implementation? What I'm proposing here with that's worked out with my colleagues is a partial timber solution where we want to combine traditional steel concrete composite in the longitudinal direction of the bridge with timber concrete composite transverse to the bridge. So looking at the cross section, we have steel girders running into the image. There are 4. And then at regular spacings, we have timber concrete composite beams running transverse. There is plywood formwork crossing across the timber beams and steel beams to act as stay-in-place formwork. And the combination of these systems allows the concrete deck to be made much thinner over the TCC spans. So there are a few advantages of this. So on top of the reduced concrete volume, the timber components are protected from the weather. The concrete deck can be waterproofed to prevent water ingress. So we can, with high confidence, guarantee a 100-year design life. And the spans take advantage of the capacity of the steel girders in the longitudinal direction. And we can take advantage of the excellent adhesion that the concrete deck has with the surfacing. Moving on to the superstructure study undertaken, what we did was say, okay, it looks like that the solution is promising in terms of reducing material quantities. So let's see exactly how much these reductions could be in comparison to more typical solutions. So we looked at a single 30-meter simply supported span and compared the proposed composite timber hybrid solution against the typical concrete super T. I should note that solution's pre-stressed, so it's not quite fair. Steel concrete composite deck and a multi-girder fully timber structure. So the objectives of this was to compare the superstructure weight per unit length, compare the life cycle carbon emissions, and compare bridge design aspects, including compliance pathway risks, peer review risks, constructability, durability, and in-service risks. The methodology we undertook was to undertake preliminary SLS and ultimate limit state design for vertical loading using the New Zealand Bridge Manual, HNHO traffic loads and dead loads. For the design of the TCC components, we use Eurocode Part 5 and assumed proprietary shear stud fasteners. And for the fully timber bridge design, we use the Mistissini Bridge in Canada to approximate the fastener and steel component quantities, as the design level we are going to was just in the preliminary design. In terms of the carbon assessment undertaken, we use the iStruct carbon calculation methodology combined with the BSEN 15987, and we did that using the one-click LCA calculator. For the materials we used, we had to make some assumptions. So we assumed the concrete was 40 megapascals, and we had grade 500 reinforcing. Hot rolled steel sections, which were also assumed to be weathering steel, XLO plates, and the glulam radiator was assumed to be H5, as well as the structural plywood. For the steel components connected to timber, we had assumed that to be stainless steel. We did not include the surfacing barriers in the carbon calculations, as we're only interested in the superstructure itself. And we excluded the site location, construction activities, and substructure as well. So from the preliminary design, these are the resulting dimensions of those different superstructures compared with one another. And one of the interesting things is that not much of a benefit is gained in terms of superstructure depth. The concrete Super T has the shallowest depth. However, that solution is pre-stressed, so it's not quite immediately comparable, as it has the extra power of pre-stressing to reduce the depth. The girders can remain at the same spacing as traditional steel concrete composite. Timber requires much more girders that are closely spaced. And we can see some benefits in reducing the total concrete thickness. We didn't reduce the thickness of the concrete deck at the cantilevers, where the exterior barriers were, as we wanted to ensure that it still has enough capacity for vehicle impacts there. Summarizing the reduction in the superstructure weight per meter and the volumes of materials used per 30-meter span, I've ranked them in terms of best to worst. And this proposed solution comes out second with a 44% reduction relative to the concrete Super T. All of these reductions are relative to the concrete Super T. The fully timber bridge, unsurprisingly, has the highest reduction. However, this is only about 12% on top of what is achieved with the composite hybrid solution. An important point with this, I guess, is for seismic design, where there's the potential for flow-on effects for reducing substructure demands and hence materials and costs of the substructure. However, that is another study to be undertaken. In terms of the carbon LCA, we found that this proposed solution could result in a 12% reduction in carbon. The actual carbon values here are not so important because they depend on many assumptions, and we did make some simplifications here. However, the trends is what we're wanting to look at. So the relative carbon between the different solutions, and the relative carbon between the different solutions and how much we could reduce in comparison to both fully concrete structure and relative to fully timber bridge. Okay. So in the findings of the carbon LCA, as well as some of the limitations, are that we excluded Module B for maintenance. And there's a couple of reasons for this. One, that there's a lot of uncertainty around the actual maintenance rates and the actions for timber components. And it's highly dependent on the efficacy of the durability detailing that we don't quite have enough data to say for sure, how good something is. The proposed composite solutions seem to be low maintenance as the timber is protected by the concrete. And as I've stated before, the concrete deck can be waterproof to prevent ingress through cracks. There's also some risk with fully timber bridges in that the carbon could be a lot higher than anticipated if performance falls below the design expectations, as well as we've found with, in New Zealand at least, for the simple timber deck bridges, timber deck over steel beams, they're found to require deck replacement every 25 years. Okay. So even though we are wanting to reduce carbon in our designs, it's important to note that this is one of many design considerations, and that we should not choose a solution simply because it is the best in terms of carbon in itself. We still have to satisfy all other design considerations. And so we can make a comparison of those superstructures that we had looked at in the previous study and compare them based on these different design considerations. And what we can see is that we can have a solution that is not quite as risky as a fully timber solution, but at the cost of not being as low carbon as a timber solution. However, as you can see, there's quite a lot of benefits relative to concrete super T and traditional concrete steel composites design. So in conclusion, a new bridge superstructure called the Composite Hybrid system was proposed, which consists of a traditional steel concrete composite main girders with timber concrete composite transverse cross girders at regular spacings. It has lower carbon than traditional options and lower risks relative to timber bridges, risks in terms of design risks, that is, and guaranteeing of performance. A comparison of different common superstructures was made based on preliminary design, where we looked at geometry, weight, embodied carbon, and design considerations. A short discussion of challenges faced by fully timber bridges was made, where we talked about issues with surfacing adhesion and sealing deck joints. And some recommendations for some future work could be looking at how to do the calculations for maintenance, Module B in our LCA, investigating the impact of a lighter superstructure on substructure design and the impacts on the substructure carbon, and lastly, fire risk mitigation and vulnerability, as well, timber is flammable, has some char resistance in big sections. However, for vehicle crashes or vandalism, we need to look into these details a bit further to ensure we don't have any unintended consequences. And that is the end of my presentation. Thank you very much for listening. I'm open to questions. Please ignore the title there. I am a bridge engineer.
Thank you so much, Ray. So I'm getting some questions in the chat. I am putting you in the organizers and panelists only chat so you can see them. And if you want, you can read it out loud and addressing them.
Okay. So I have one question. Will carbon footprint be one of the main considerations in bridge design soon? I guess this will be something that would be set by design standards. I see it as one of the many design considerations we have. Will it be the main one to consider? I don't think. In a hierarchy, we could put it slightly higher up. However, we need to make sure that the solution we're providing is the best in all of the considerations. Good question too. Good presentation, Royce. Can you please explain why you didn't consider Module D when assessing the LCA and the outcome of that omission? Yes. So Module D, I believe, is recycling. I do have one more slide where I did include, so in the slides before, I did not include Module D. It was Module C where we had looked at including or excluding for the biogenic carbon. In terms of your Module D in itself, it does reduce the amount of carbon, as you can see, for all of the superstructure types. However, there's some uncertainty around exactly like what really happens to the materials from bridges in recycling them. Okay, so which software did you use to make comparisons between materials? AutoCAD. In terms of the carbon calculation, that was the one-click LCA carbon, if that helps. I only used AutoCAD for drawing the cross sections to scale. Question 4. Has any design projects been constructed? No, we haven't gotten any bridges using this proposed composite timber hybrid yet, but we are looking for a bridge to implement this on to see how it goes in practice. Hi, Royce. Good presentation. have you also considered doing a cost comparison of your superstructures in the future? Yes, this is something that we did try to implement before writing this paper for a Timber conference. I can make the paper available on the global PAN. However, yeah, we ran out of time and some budget as well. It is still something that we do want to pursue. Any other questions?
Not for now. I think we can wrap up, and thank you so much, everyone, for joining. If you want to say just a few words to close the session.
Radio. So thank you everyone for coming and listening. I hope you had enjoyed this session. The proposed solution is not the, be all and end all. It's just one of many possible ways to try and get timber into our bridges in a practical manner without having to wait on changes to codes or push from clients. Thanks.